Now, we are going to continue with the explanation of the model. So why do we need a model to study a system? Now, as we have said, we can study a system through direct experimentation. But this may not be the option at all times. Why? Because the system may not exist yet. Okay? For example, you are going to open a new supermarket into your distribution network, and you want to try if it is going to have a good performance, it is going to show a good performance or not. Now, you cannot study this, you cannot practice this until you open the supermarket, right? So you do not know what's going to happen. But if you use a model of your distribution network by introducing this new supermarket into your distribution network, you can try to see what happens through an experimentation over the model. Or it may not be practical to experiment in the system. Even if the system exists, it may not be practical. As I have told you, you are trying to, for example, experience a new service policy in a bank. So you cannot just say to your customers, we are trying a new policy today. It is just an experiment. I don't know if you are going to like it or not, but today is going to be like this. So this is not possible in usual cases. So sometimes the system may not allow experimentation as well. Because of that reason, most studies on real systems requires a model of this system. What is a model? A model is defined as a representation of a system for the purpose of studying the system. Okay, we are trying to study the system. The purpose is this. So we are defining a representation of the original system. So it is just an imitation. Okay, it is just a fake version of the system, and that imitation or fake version can be created in different environments. A model should consider only the aspects of the real system that affect the problem under investigation. Now, you cannot put every detail into a model from the original system. So first of all, we need to define a problem that we are trying to solve. So there's a problem in that system that we want to solve. And if we want to solve this problem, and if we want to make experiments over a model, then we should only put the aspects of the original system that are related to the problem. So if you try to put every detail into the model, then you are going to make the model too complex. For example, if you try to develop a model for the banking system, you can define many attributes for the clients. As I have said, the balance in their accounts can be an attribute. This is defining the entities. However, if you are also trying to model their genders, okay, trying to put attributes related to genders, this is irrelevant to the problem, right? So it is just going to make it too complex. Why should we take the aspect of the original system which is not related to the problem that we are trying to solve? So a model should also be sufficiently detailed to permit valid conclusions about the real system. So I'm not saying that it should be too simple as well. You should put everything that is relevant to the problem into the model, so it should give you valid results. The results that you get from the model should be very similar to what would you get from experimentation on the original system. So we should say that the model should also be detailed enough to be a valid model. And if the purpose of investigation changes, if the problem changes, then we need to change the model as well. So if you are going to develop a model for a system, first you need to know your problem. This is very important, my friends, at this point. Please understand this. If you want to create a model, simulation, a spatial simulation model, because it is going to take a long time to develop it, if you are going to invest in such a thing, please first define your problem. Everything depends on the problem definition. A model of the system has the same components as the real system. For example, it has entities as well. It has attributes. It has state variables and events and activities. But we just take these components if they are relevant to the problem, okay? So not every detail, not every attribute, not every event, not every activity is going to be taken from the original system. For example, if you intend to create a model of the solar system, can you put all details in the solar system into it? Or if you try to create a model of a cell, human body cell, Can you put every detail that is going on there? It is impossible for you, okay? I mean, we do not have knowledge about these systems at that amount, right? So if we are going to solve a problem related to these systems, and if we are going to make experimentation on the models, then we are just going to create a model with components which are relevant to our problem. Now, there are several types of models. For example, a physical model is either a larger or a smaller version of an object. So if you create a physical solar system model in a laboratory environment with your marbles, that physical model is going to be a smaller version of the original solar system. However, we can also create larger models as well. I mean, imagine the other example, the human body cell. Human body cell is very small. I mean, you cannot even observe with your naked eye. So what you are going to do is you are going to create a larger version of it as a physical model, right? So, but as industrial engineers, we are usually using mathematical models. Mathematical models, they use symbolic notation and mathematical equations and inequalities to represent a system. For example, a set of differential equations is actually a mathematical model of a dynamically changing system. Or let's imagine a linear programming model. Okay, so linear programming model is doing what? It is using inequalities as restrictions, and again another equation as an objective function, right? So it is just trying to model a problem related to a system. Now, a simulation model is also a particular type of mathematical model of a system. So though we are going to practice simulation models over softwares, actually what the software is doing is to create a mathematical model of that system. So do not forget about it. A simulation model is actually a mathematical model. Now, we can also classify the simulation models. So we can say there are simulation models either static or dynamic. Okay, what is a simulation model and what is a dynamic simulation model? So static simulation models represent systems at a particular point of time. Now we are going to perform a simulation of a newspaper stand. Let's just say newspaper stand. Whatever happening throughout the day is irrelevant to our problem, right? I mean, what is important in a news vendor is how many newspapers that it has sold in the end of the day. Okay, so if we are going to create a simulation model of the system, we are just going to simulate what happens in the end of the day. Okay, so what was the total demand in the end of the day? How many newspapers we had in the end of the day? So we can directly study that time point. Instead of the occurrences of the sales or the arrivals of the customers, we are not interested in any of them. We are just interested in the daily profit, which occurs in the closing time. So for this system, we can create a static simulation model. The total newspaper sale in the end of a specific day. So we are just interested in the end of that specific day. So we need to create a static simulation model here. We should not observe the dynamic behavior of the system throughout the day. But in dynamic simulation models, we represent system as they change over time. The system variables are changing over time dynamically, and we are interested in the observation of these changes. So the progress of newspaper sales at the newspaper stand between 9 a.m. and 4 p.m. So at which hours the customers are coming more frequently. If we are interested in observing these kind of behaviors, then we need to build a dynamic simulation model, a model which is observable through time. Okay, so that is the difference between a static model and a dynamic model. Now we can also classify simulation model in a different perspective. We can also call them deterministic or stochastic. Now every model of a system has input variable. These input variables can be random or deterministic. Imagine this clinical system. In a clinical system, you give appointments, you assign appointments to the patients, right? And assuming that the patients are always coming on time, then the arrival of the patients into this system is going to be a deterministic input. So we know exactly how much time that we are going to observe between consecutive arrivals, okay? Or if we are talking about an assembly line, the tasks that are being performed by robots in that assembly line are going to be deterministic, because for each product, they are going to exactly spend the same amount of time. Unlike the two ordinary workers, the robots are going to spend exact same time for each product. So the time for that activity is going to be a deterministic time. Okay, it is already known. So if the input variables of that model are already known, then we call that is a deterministic model. And in simulation, that we may also have deterministic simulation models as well. Now, in stochastic simulation models, which is usually the case, okay, we usually observe stochastic simulation models, the input variables are usually counted as random. I mean, even if you intend to simulate a clinic with an appointment system, again, there will be some deviation on the arrivals of the clients from the appointment time, right? So that deviation is random, and you do not have a control over it. In fact, you cannot model it because it is too complex to model, because that deviation is caused by the system environment. I mean, we cannot model the influences that creates the deviation of the arrival time of the patient. Okay, there may be too many reasons there outside the system. Traffic congestions, other delays, etc., etc. So we cannot model such deviations with a deterministic simulation model. So we are just going to assume there is a deviation, and it is a random deviation, and it follows some probability distribution. Or imagine a bank system again. Servers are serving to clients, and two different clients are trying to get a different type of service, right? So we cannot know every detail about the service that each client is going to require. So we are just going to assume that the service time for any client follows a random distribution. So the inter-arrival times of the clients or the service times of clients, if they are going to be modeled as a random input that follows a probability distribution, then we call this stochastic model. Now, if there is at least one random input in a model, let's just say every input is deterministic except one. One of them is assumed to be random, then we call that simulation model a stochastic simulation model. So if you want to have a deterministic simulation model, all inputs should be deterministic. Finally, a discrete or continuous simulation model we may have in the third classification. Just like the systems, the models can be discrete model or a continuous model. As I have told you, if all of the state variables are changing a discrete set of time points, then we call this system a discrete system. Okay, the events are occurring at discrete set of time points. Basically, what I'm saying is, if the events are countable, okay, if the events over time are countable, if you can count the events, for example, you can count the arrivals, right? You can count the departures as well. If the events are countable, then usually that system or that model is discrete, okay? But if the events are uncountable but measurable, okay, if the events are uncountable but measurable, for example, the rain event, can you count the drops, raindrops? It is impossible, right? So what you can do is you can measure the rain amount. So in that case, that system or the model of that system should be a continuous system of continuous model, okay? Now, if you check the last sentence in this page, it says most simulation models are discrete, so the events are occurring over discrete set of time points, because modeling continuous systems or creating continuous models is not very easy. It is very complex. Most simulation models are discrete, and stochastic because there are too many inputs which should be counted as random, which are too complex to model to deterministically. So stochastic models are much easier to model. And dynamic, because usually we are also interested in the behavior of a system over time. The problem is usually related with the behavior of the system over time. Therefore, these simulation models are dynamic as well. So discrete, stochastic, and dynamic. Okay. So most simulation models we observe, but of course, there are other examples as well. So this is just a case where we observe mostly. So we define simulation models. First, we classify simulation models or static or dynamic. Now, first of all, static simulation models cannot be discrete or continuous because they are static, right? So if they are static, we cannot talk about the time points where the events are occurring because there's only a single moment in that simulation model. So because of that reason, the static models cannot be discrete or continuous. Now, a static model can be either deterministic or stochastic. For a static simulation model, if the inputs are stochastic, then a stochastic and static simulation model is called Monte Carlo simulation models. Okay, the type of simulation that we are doing here is the Monte Carlo simulation. Okay, but in this course, we are going to be usually interested in dynamic, stochastic, and discrete simulation models. Okay, so dynamic simulation models can either be deterministic or stochastic, and whether deterministic or stochastic, they can be discrete or continuous. We are going to be mostly interested in discrete, stochastic, and dynamic simulation models, which are going to be called discrete event system simulation models. Okay, so that is the last header of this presentation file. What is a discrete event system simulation? A dynamic, stochastic, and discrete type of system simulation is basically a discrete event system simulation. We are going to explain this final part in our next video.